So this video is in regards to the electric field. Now we saw that two charges that are at a certain distance between each other uh, are experiencing a force. So those forces are experienced as a result uh, of the objects, the charged objects, are not in contact with each other. And in order to explain why those forces exist, the concept of field helps us. So we saw the concept of field in gravitational field when we were talking about the universal force of gravity. So we saw that every object that has a mass is surrounded by an area that if you place a similar object on it, in that case would be an object with a mass, an interaction will happen. So in other words, this is the concept of field. In the translation that we do into the electric field is that if we have a source, a charged, so like a charged source, then this is surrounded by an area, so that if we place a similar one, and in this case will be another charged object on that area, an interaction will happen. When we talked about the gravitational field, the interaction is always attraction, and it is attraction toward the center of the source. But when we have a charged object, that depends on what is the source, nature the source has, and what nature the charged object that you are placing into that field has. Field is a vector quantity. What do we have to keep in mind in terms of the field? Field is a vector quantity, which means that it has magnitude and direction. The same thing that we did at the gravitational field, we see and define the configuration of the field. And the way that we do it, remember what we have said in gravitational field, is by placing a test object. Now, what do we have to keep in mind when we are using that concept that we learned on Physics 20 and implementing it in Physics 30? We have to keep in mind several things. The first one is that the source can be positive and negative. So the source can be an object that is positively charged or negatively charged. So therefore, in order to identify the configuration of the field, electric field, we have to put some conditions in terms of the test object. And the condition that we put into the test object is, remember what we said in gravitational field, that we said the mass of the test is way, way smaller than the mass of the source. So the conditions for test charge are one, the charge of the test object has to be way, way smaller than the charge of the source. Of the source. And another thing that in order to keep control of the test object, the test object is always positive. Positive charge. So in this case, we see the interaction of the source that can be positive and negative, and the test charge that it is way smaller than the source in magnitude, and it is always positive. Okay. In the gravitational field, we don't have to state this condition, the second condition, because mass is a scalar quantity and it is only one, like it's a number. Okay. So now let's see and discuss the configuration of the field, the electric field, when we have a positive source and a negative source. So if start with a positive source first. That means that you will have a source that is positively charged. Now we said that the source is surrounded by an area, so that if we place a test or a similar object in this area, then we will see an interaction. Now what do is we place a test object or a test charge, and the condition for the test charge is positive, and the magnitude of the test is way smaller than the magnitude of the source. So now we see what is the interaction that is happening between the test charge and always positive and the source that in this case is positive. And since they are two like charges, they will repel each other. Okay, now we put the test somewhere in here, and then we see what is the interaction. They will repel, and then they will repel. So anywhere that you put this test charge near the source, positive source, you will see a configuration like this, configuration of the field like this. Now those lines are known as the field lines. And when we are drawing this, what it means is that the stronger the field, the closer the lines. So stronger the field, stronger the field, closer the lines. So this is telling us that when we are close to the source, in this area A here, we have a stronger electric field than when we are at area B away from the source. So from this explanation, we can say that the electric field strength decreases as it is going away from the source. So when it is going away from the point source, then the electric field strength is decreased. Okay, so now let's take a look and see how the electric field strength will look when we have a negative source. So if we have a negative source, point source, then we said that it is surrounded by an area where the So it is surrounded by an area, so that if you place an object, a similar object on that area, an interaction will happen. In order to identify the configuration of the field, what we will do is we will put a test charge. And remember what we said in terms of the test charge. It has to be always positive, and the magnitude is way, way smaller than the source. So then we see what is happening. So now when we place the test charge here, and we see the interaction between the source, that is negative in this case, and the positive, always positive test, the configuration or the interaction will be attraction, because they are opposite charges. Okay, so then you place the test somewhere in here, and you'll see that is attracting as well. So again, this is the configuration of the negative source, which is very similar to the configuration of the gravitational field. And again, we notice the same thing, that closer to the source, the surface of the source, the field is stronger than away from the source, which is area B in this case. So we see that as the distance from the source is increased, the electric field strength is decreased. So now, if we summarize what we have said up to now, we can say those three things for the electric field. The electric field can be produced from the positive and negative sources. The electric field is decreased as the distance is increased. Distance from the source is increased. And like any field, electric field is a vector quantity. So those are the two or three quantities or three qualities that electric field has. Okay, now how do we calculate it? What is the formula? This is logic now. We need some formula. Now, the formula to calculate the magnitude of the electric field is electric force, magnitude of the electric force over the charge. The units that we use for the electric field strength are newtons per coulombs, because force is newtons, charge is coulombs. Okay, now this is when we know the electric force. We are using the magnitude formula, the formula for the magnitude, because the direction of the electric field will be defined by placing the test charge and by considering the charge of the source. So here you start working on two directions, I should say. One that is that you are dealing with a vector which has magnitude and direction. So then the magnitude is calculated in one way and the direction is calculated in another way, is figured out in another way. When we know the force and the charge that we are placing into, into the field, then we use this formula. And if we know the distance that we are measuring the electric field strength and the source, then the electric field strength is calculated as K, Q of the source over R squared, where K is Coulomb's constant, Q of the source is the charge of the source, the magnitude of the charge of the source, and R is the distance from the center of the source to the point P that you are measuring the electric field strength. So depend what do you have in your equation or in your problem, which equation are you using, either this one or this one here. So if we have, let's suppose, a charge that is placed in an electric field, and let's say that the mass of the charge, so let's say that we have a charge that is placed in an electric field, and the charge is 90 mu coulombs. Mass of the charge is 0.35 milligrams, and it is experiencing an acceleration as a result of the presence of the electric field. It is experiencing an acceleration of 1.25 times 10 to the power of 5 meters per second square. What is the electric field strength at this point? Because the we are assuming here that the acceleration is just as a result of the electric field, not any other forces that the object is experiencing. So now, based on the second law of Newton, we can find that the electric field, which in this case we are considering to be equals to force net, is equal to mass times acceleration, or 0.35 times 10 to the power of negative 6 kilograms times 1.25 times 10 to the power of 5 meters per second squared. So the electric force, which, as we said, is equal to the electric field, based on the calculations on your calculator, will be 0.04375 newtons, or you can say it is 4.38 times 10 to the power of 1 to negative 2 newtons. Now, this is the force that the charge 90 mu coulombs is experiencing as a result of the source that is there. Now, if we are finding the electric field strength, then we will use the formula that electric field strength is equal to electric force over Q, and those are magnitudes, so I'm not writing those vertical lines, but I'm just saying the magnitude here. So this will be 4.38 times 10 to the power of negative 2 newtons over 90 times, when we convert new coulombs into coulombs, so then we will have times 10 to the power of negative 6. And you'll have that conversion into your formula sheet. So 90 times 10 to the power of negative 6. Use brackets. Do not be afraid to use brackets. So then we will have that the electric field strength is 4.86 times 10 to the power of 2 newtons per coulombs at that point. So now let's see and calculate the electric field strength, or yeah, let's see and how can we manipulate and figure out either which formula are we using, or what is the, or how can we manipulate finding the source and all that stuff. So let's work now on another example where we are calculating the electric field strength of point source that has a magnitude of positive 3.20 times 10 to the power of negative 6 coulombs, or 3.20 new coulombs. That is at a point P that is at a distance of 2.50 centimeters from the source from the center of the source. So this is the source, and what we are doing is something like this, the situational diagram. So we have a positive source, and the point P is to the right of the source. So the distance between the source, center of the source, and the point is 2.50 centimeters. So what you have to imagine are those steps. You're placing at point P a test charge, which is always positive. So now the electric field strength at this point will be, or the interaction is what? Attraction or repulsion? It's repulsion, okay. So then the electric field at this point will be this one here, and the magnitude of it will be kq of the source over r squared. So as a vector, this is what I said before, that when you're calculating or you're figuring out the electric field strength, you are using one way to figure out direction, and that way is placing the test charge near the surface of, near the or at the point, and then looking at the interaction, and that will be the direction, and the magnitude either using Fe over Q or KQ source over R squared. And in this case, you will use KQ source over R squared because you don't know the force. So now the magnitude of the electric field strength at that point will be 8.99 times 10 to the power of 9 times the source, magnitude of the source, 3.20 times 10 to the power of negative 6 over 2.50 times 10 to the power of negative 2, the whole thing to the power of 2. So when you enter this information in your calculator, you will have 4.60 times 10 to the power of 7 newtons per coulombs. Now let's see an example when we have to find what is the source, the charge of the source, when we know the electric field strength. So if an electric field strength is 7.0 times 10 to the power of 8 newtons per coulombs, and it is toward point charge, so it is toward the point charge at a distance that is 4.80 centimeters from the source of the center of the charge. What is the magnitude and the sign of the source? So the situation is something like this. You have a source here, which you don't know what is the nature of it, and then you have a point P that is at a distance from the center of 4.80 centimeters, what do you see is that the electric field is toward the source. So this is the electric field toward the source, and the magnitude of it is 7.0 times 10 to the power of 8 newtons per coulombs. So now we are looking for what is the source. First of all, what do you think that the source, the nature of the source is positive or is it negative? Knowing the fact that the electric field is toward the source. In other words, you have to think, you know that this is always positive. What is causing, what is the nature of the source, positive or negative, to cause an interaction of attraction? And it should be a negative. Good. So now let's figure out the magnitude of the charge of the source. We have this K, Q of the source over R squared. From here, we can find that Q of the source is electric field strength at that point times the distance squared over K. And in our case, will be 7.0 times 10 to the power of 8 times 4.88 times 10 to the power of negative 2, the whole thing to the power of 2 over 8.99 times 10 to the power of 9. Enter this in your calculator and you should have a value that is 1.79 times 10 to the power of negative 4 coulombs. Make sure that when you're entering it in your calculator, you're using brackets or proper notation in your calculator. Okay, so this is the end of the video for the part where we are discussing the electric field of a point source. So you should be able to know how to calculate the electric field of a source given and the distance at any direction. So direction and magnitude. Keep in mind what we said in terms of the electric field in general as being of a point source, or being positive and negative, what is happening, and the negative that is very similar to the gravitational field strength. When the field lines are close to each other, then the field is stronger than when the lines are apart from each other, like in this case here. That means that as we are going away from the source, that the electric field is becoming weaker and weaker. And how to calculate the source and the nature and the magnitude when we know the direction of the electric field at a point nearby the source. So this will be the first part of the video.